The web is so vast that light has been traveling for over 13 billion years. The universe has been growing and, consequently, the light has been extending from the most far-off worlds. We're looking back in time, almost to the Big Bang. The vastness of the universe could appear huge, but every single piece of it started from what we allude to as the singularity. This is how we interpret the Big Bang theory. At any rate, the James Webb Space Telescope, JWST, has uncovered huge secrets about the birth and advancement of the universe, leaving us confounded. Renowned physicist Brian Cox has declared that the striking discoveries made by the JWST could reshape our view of the universe in general. Join us as we dive into these new heavenly revelations that promise to disturb our understanding. The James Webb Space Telescope, named after the distinguished NASA administrator James E. Webb, stands as a marvel in modern cosmic exploration. This telescope represents an immense technological leap forward from its predecessor, the Hubble Space Telescope. Coming to fruition due to a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST outperforms its predecessor in many ways. It uses cutting-edge technology and a design optimized for studying the universe in amazing detail. Unlike Hubble, the JWST delivers clear and sharp pictures of far-off celestial bodies working primarily in the infrared range. This unique feature allows it to penetrate massive dust clouds and capture celestial objects that were previously hidden from our view. With its tremendous 6.5-meter primary mirror made from 18 hexagonal segments, the JWST dwarfs Hubble's mirror in size. Located about 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in harmony with Earth, ensuring a stable and continuous view of the universe. While investigating the far-off corners of space, studying light years away also involves a form of time travel. The JWST uses infrared instruments to observe celestial objects and events from billions of years ago. The light emitted by these objects due to the expanding universe undergoes a redshift shifting from the visible spectrum to the infrared spectrum or longer wavelengths. Luckily, the JWST can detect infrared light emitted by celestial bodies at extreme distances, enabling scientists to study the birth of stars, explore galaxy formation, and examine exoplanet climates. Its most recent outstanding discovery includes identifying a huge mass of galaxies at the edge of the observable universe. This finding challenges the validity of the Big Bang theory, prompting a reassessment of our fundamental cosmological assumptions. A short journey through the history of space exploration. To better understand how we arrived at this point, let's take a short journey through the history of space exploration. Early developments by the Greeks and Chinese laid the groundwork for understanding planetary motion by observing celestial bodies. In the 17th century, Newton's laws provided a theoretical framework for space travel. In the early 20th century, Edwin Hubble, a renowned astronomer, made groundbreaking discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were actually separate galaxies far beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law showed that galaxies farther away were receding at higher rates, providing evidence for the expansion of the universe. The post-World War II era marked the beginning of the space race, with the Soviet Union's launch of Sputnik in 1957 as the first artificial satellite in orbit. Yuri Gagarin's orbital flight in 1961 and the Apollo 11 moon landing in 1969 were landmark achievements. Fast forward to 1990, when the Hubble Space Telescope, HST, was launched, providing remarkable clarity and dazzling insights into the universe. The transition from early observations to the technological marvels of the JWST highlights the ongoing improvement in our understanding of the universe. The Hubble Space Telescope's legacy. The HST uncovered the vastness of space and transformed fundamental ideas in cosmology. Take, for example, the famous Pillars of Creation image in the Eagle Nebula, revealing a stellar nursery formed by large columns of gas and dust. Another key achievement was the Hubble Deep Field, capturing thousands of galaxies in what appeared to be an empty patch of space. The HST also delved into exoplanet environments, pinpointing components like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the discovery of the nearest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These achievements solidified the HST's legacy as a foundation of modern space science, captivating the world with its stunning cosmic revelations. The JWST was launched to build on technological advancements and lessons learned from Hubble. One key area where the JWST is making waves is in the study of exoplanets. While Hubble was instrumental in detecting and studying some exoplanets, it was limited in its ability to analyze their atmospheres in detail. The JWST's infrared sensors can examine the composition of exoplanet atmospheres by capturing the starlight that filters through them. This allows scientists to determine the presence of molecules like water vapor, methane, carbon dioxide, and even potential biomarkers clues that could indicate the possibility of life. Additionally, the JWST is transforming our understanding of star formation. Stars form within dense molecular clouds, often obscured by dust and gas. With its ability to detect infrared radiation, the JWST can peer through these clouds, revealing hidden star-forming regions. This is crucial for understanding how stars and planetary systems form, evolve, and eventually die. By observing the early stages of star formation, the JWST provides insights into the fundamental building blocks of the universe. The study of black holes is another area where the JWST is making groundbreaking contributions. Supermassive black holes reside at the centers of most galaxies, exerting a powerful influence on their surroundings. The JWST's high-resolution imaging allows scientists to observe the effects of black holes in unprecedented detail. By studying how black holes interact with their host galaxies, the JWST may help us understand how they influence the growth and evolution of galaxies over time. Moreover, the JWST is exploring the cosmic dawn, the period shortly after the Big Bang when the first stars and galaxies began to form. This era, occurring roughly 200 to 400 million years after the Big Bang, remains shrouded in mystery. The light from these early galaxies has traveled billions of years to reach us. The JWST's ability to detect faint infrared signals provides a glimpse into this primordial time, leading to discoveries about the first galaxies, their formation processes, and the early evolution of the universe. As the JWST continues its mission, its discoveries will challenge existing theories and encourage new models of cosmic evolution. Each new image and observation expands the boundaries of our knowledge, bringing us closer to understanding the origin, structure, and future of the universe. The telescope's ongoing mission promises to uncover hidden corners of space and provide answers to questions we've only begun to ask. With its cutting-edge infrared technology and groundbreaking discoveries, the JWST has opened a new chapter in the exploration of our universe. The revelations it continues to uncover will shape the future of space science and lead to new paradigms in our understanding of the cosmos. One of the JWST's most startling discoveries is the presence of massive galaxies forming much earlier than expected, just a few 100 million years after the Big Bang. These galaxies appear far more evolved than current models predict, forcing scientists to reconsider fundamental assumptions about the universe's early development. For decades, the lambda-CDM model, lambda cold dark matter, has been the standard framework for explaining cosmic evolution. This model suggests that dark matter and dark energy play dominant roles in the structure and expansion of the universe. However, JWST's findings of unusually large and mature galaxies in the early universe challenge these predictions. Some scientists propose that either our understanding of galaxy formation needs revision or that the early universe evolved differently than expected. Others speculate that we may need to rethink aspects of the Big Bang theory itself. Could there have been an even earlier cosmic phase before the Big Bang? Could unknown physical mechanisms be accelerating galaxy formation? While these questions remain open, the JWST has already reshaped the conversation on cosmic origins, a sign that our understanding of the universe is still evolving. One of JWST's most revolutionary capabilities lies in its detailed atmospheric analysis of exoplanets. While Hubble detected exoplanets and provided insights into their atmospheres, its visible and ultraviolet spectrum had limitations in identifying specific molecules. The JWST's infrared instruments allow it to detect and analyze key atmospheric components such as JWST recently observed WASP-39b, an exoplanet 700 light-years away, detecting carbon dioxide in its atmosphere with unprecedented precision. This marks a new era in studying exoplanetary atmospheres and brings us closer to identifying worlds with conditions suitable for life. One of the biggest questions in astronomy is, are we alone in the universe? While JWST is not designed to detect direct evidence of alien life, it can identify the chemical fingerprints of biological processes. Scientists are particularly interested in